I found when varying with respect to G alpha beta was del alpha x mu del beta x mu is equal to half of G alpha beta and then del alpha x mu del alpha x. The raising is raising with the square sheet matrix G. That's what I found. This is the equation of motion with respect to G. Okay, now let's take determinants on both sides. Okay. We're writing on minus signs at the moment. That's always tricky. But ignoring minus signs, we get a determinant of this object of del alpha x mu del beta x mu. Now what? We've got this as far as the matrix structure is concerned is a constant. It's 2 by 2 matrix, so the determinant is multiplied by constant square. Okay, so we get is equal to half square, so that's 1/4, times del alpha x mu del alpha x mu opening square times det of G. Okay, now we want to go minus signs. You see, we know this. We want a minus here, but we also want a minus in the det of G. So make it minus G. And then we get square roots of both sides. Okay, so we get square root of this is equal to half. We take a positive square root. We take a positive square root, and with our sign convention, this object without the square is a negative definite number. Okay, so we get minus. Okay, and square root. Okay? The minus sign is because, our sign convention is
minus plus.
Right, so the time derivative is negative of the space derivative. Okay? But the time derivative always dominates the space derivative. The time derivative is energy. Space derivative is momentum. Energy is always larger than momentum. So in our sign convention, this quantity as written is a negative quantity. Okay? So we've got a positive number, we're taking its square root, and we're using the convention of the square root. Square root has two possible values, plus something or minus something. We're using the convention that we get the positive number, the positive object. Okay, that's what we mean by modulus. So that's why I put the minus. Is this clear? I mean, it's just a matter of convention. Okay, so therefore, this thing, just to say it again, this is going to have a kinetic term, and the kinetic term in this action will be positive with the structure sign.
So, I think this will do it in that expression that you started off. Otherwise, this is oh, okay, you raised it.
I'm raised. Okay. Therefore, we find that this action is the same thing. This half is this half. It's minus of this sign as that. Just by substitution. Is this clear? Well, we wanted yeah, I'll do the minuses match. Sorry. Okay, good question. Do the minuses match. We have written the minuses don't match. So let's see. This. Let's say that's wrong. Okay, sorry. Okay, let's see. We want something that is positive.
Minus sign won't be there on the right hand side.
You're saying minus sign won't be there on the right hand side. Possibly,
because we took a square root of the thing, so there are two signs possible. So the one with positive will make the action positive.
Yeah, it's not so clear to me actually, because of our sign convention we had negative type derivatives.
Yeah, but there is a minus sign again in push.
Okay, yeah, of course, in taking the square root we have this plus minus ambiguity. Sorry, just a minute. Sign. Was this the right sign to start with?
But this you want the 90% positive difference.
And certainly this is the right. Certainly we want to get this, because otherwise it won't make sense. These two signs have to be the same. But what's looking puzzling is that if by the square root we mean the positive square root, this looks like a negative definite object, whereas this looks like a positive. Yes. I should both have. I should have both as C. Okay, so at this stage when taking the square root we have plus minus ambiguity, we choose one of the signs that works right. I can't think of at the moment the rationale for this particular sign. It actually doesn't matter, because all we really care about is that the equations of motion are the same, and this guarantees that anyway. But there is something slick to say about why you get this sign. Let's not do it online here. Let me try to get that next time. Signs are always okay, fine. So modulo of this sign, we've found that this action is the same as this action. Is this clear? Okay. Now all this is very slick, but it's hidden something quite important, and it's this hidden thing that I want to emphasize. Okay. The question we're going to ask is this system the same classical system as this system? By which I mean, is there a one-to-one map between solutions, the solutions of the two theories, such that, anything you compute with this solution is the same as you compute with that solution. Okay. In order to answer that question, well, in order to answer that question, it's interesting to do the following thing. You see, to start with, the structure of these equations looks as follows. It looks like we've introduced three new variables, the g alpha betas, but we have three new constraints from the equations of motion with respect to for g alpha beta, which allowed us to determine what g alpha beta were in terms of the x's. Plugging that solution back in, you get some equations of motion purely for x's. Therefore, it looks like these, which would be the same as the equations of motion that you derive from the x theory, because we got the same action, modular sign, but that doesn't matter for equations of motion. Okay? Therefore, it looks like we've got the same classical systems. However, this is wrong. What I said was wrong. Does anyone know why it's wrong? Can anyone see why it's wrong? Okay? It's not true that all three of the new additional degrees of freedom that we've got from our system are determined. No, it's not true that all three g alpha betas are determined by these equations of motion. How do we see that? Well, one way of seeing that is by taking the trace of these equations. Taking this equation and multiplying it with a g alpha beta with other signs. With others. Okay? On this side, what do we get? We get del alpha x mu, del alpha x mu. And on this side, what do we get? This just becomes 2 because it's trace of 2 cross 2 matrix. And this is the same thing. Del alpha x mu, del alpha x mu. So what we've got here is an identity. So we thought we had three equations here. I mean, it was a matrix set of equations. Okay? We thought we had three equations from the two diagonal components and the one off diagonal component, symmetric just 3. But actually we see we only have 2 equations. Because one of these equations is just identically satisfied. It's not giving you information about G, it's just a trivial identity. okay, what's going on? We've introduced 3 new degrees of freedom, but we've only got 2 new equations. And we've only got 2 equations, so only 2 of these, and you can easily check that the other 2 equations aren't true. Okay? So 2 of the 3 new degrees of freedom that we've introduced is determined by this constraint equation that we found. But the third one is not. Given that, how did it happen? Given that, how did it happen that we managed to get the same actions of the 2 sides? Well, what happened to that third free degree of freedom? Since we got the same action, we got an action plugging in with this equation of motion that didn't depend on this third free degree of freedom, it must be that third free degree of freedom just doesn't enter the action at all. Okay, let's see how that works. Let's look at this action here. Okay, now consider 2 different metrics. G tilde, which is equal to G alpha beta, times G alpha beta times e to the power phi. Okay, where phi is an arbitrary function of your Winchie coordinates. Okay, now under this transformation, what happens to all the fields that enter this action? Well, square root minus G alpha beta tilde alpha beta is equal to e to the power 2 phi by 2. The 2 phi is because the determinant scales like a square, and the by 2 is because we take the square root of square root G alpha beta. But also G inverse, so G alpha beta tilde is e to the power minus phi G tilde G alpha beta. Now this action has both the square root determinant as well as the G alpha beta. There are no derivatives anywhere, it's metric. Okay, so you plug this in and you find you get exactly the same action for G and G tilde. Okay, so there is a huge symmetry in this action. Okay, the symmetry has a name, it's called Weil symmetry. So this action has a symmetry on the Weil transformations. Okay, 2 different metrics that are related to each other by rescaling with a function of worldsheet coordinates give you same functional form of the action. Okay, it's because the action has this Weil symmetry. It's varying with respect to this direction in field space. Gives you no equation of motion. And varying with respect to this direction in field space, you can easily convince yourself it's the same state of the trace of these equations. Because you're varying with respect to the direction in field space in which the whole metric is changing in an overall way, which you can convince yourself is basically the trace of this equation. This equation of motion came from varying all the components separately, but if you varied in a way that was proportional to the metric, it would be G alpha beta, the thing that Floating-Point had. The variation is proportional to delta G alpha beta is proportional to G alpha beta, and therefore that traces this equation. Okay? So we've discovered the reason for our equations of motion being too few to solve for this new degree of freedom. The reason is that the action we wrote down, this new fancy action we wrote down, had a big symmetry. Now what is the consequence of this? The consequence of this is that as we have seen, if we are given a solution to the equations of motion that come from this action, that solution determines 2 of the 3 components of the metric G alpha beta, but the third component is completely arbitrary. Okay? As far as this action is concerned. So, strictly speaking, as dynamical systems, these 2 actions are not the same. For every solution to the equations of motion here, there's an infinite number of solutions to the equations of motion here. There means solution with any given metric times all possible Weil transformations. Is this clear? Okay? So, while a naive manipulation leads you to seems to imply that this action and this action are the same classical systems, that is not quite true. There is an infinite number of more solutions to the equation of motion of this than of this. Okay. Now,
extra degrees of freedom is not dynamical. So
it's not dynamical, but if you try to do a quantization of the system, system, you see, quantization is quantization of phase space, and you would find a huge additional, a much larger phase space in the second system. Okay, but your point is completely right. It is now dynamical, and that's what we're going to use. So hang on to 2 minutes. It's completely correct. Okay. The comment made was that even though we've got lots of degrees, new solutions, these new solutions are each related to each other by symmetry. So how do we make these two dynamical systems the same? We make these two dynamical systems the same if we supplement this theory by a statement. The statement that we are going to take the symmetry and gauge it. Okay? Take the symmetry and treat solutions that are related by Y transformations as the same solution. Once we do that, we make the two dynamical systems the same. Is this clear? Okay. Now, you see we have now increased the gauge invariance in our system. In the original action itself, we had a reparametrization invariance, and we agreed last class that we should be thinking of the system as being gauged by this reparametrization. Two solutions that differ only by reparametrization are the same solution in space-time, same physical motion in space. Now, once we've gone to this new form of the action, this form of the action, we have inherited a third gauge invariance. Two solutions should be regarded as the same physical solution if they differ by either reparametrization invariance or by wire rescaling. Okay. It is with this understanding that this action is the same as this action, as a classical dynamical system. Is this clear? Okay? So it is this understanding that we're going to keep in our mind now, in order to try to make a quantum theory, starting with the second action, which is a much easier job than starting. Is there clear? Any questions or comments before we proceed? Okay, so let's move on. So let's clear everything and write a little more systematically. Now our plan for this lecture, by the way, just one comment about schedule. I realized that there were conflicts on Tuesdays. So we're back to our Wednesdays and Fridays schedule, okay? Wednesdays and Fridays, that's written in stone, unless there's a really good reason we won't change it. Okay? Fine. So what we're going to do in this lecture and the next one, and perhaps the next one, is perform an honest quantization. Perform a quantization of this action, the string action. We're going to do this in 2 steps. In this lecture, I'm going to try to get to the result as fast as I possibly can, using slightly slipshod techniques. We're trying to be as honest as we can. In the next 2 lectures, we'll go over. Well, it may take a little more than the next 2 lectures. But in the next few lectures, we will go back and revisit the question and discuss it very carefully, using advanced and interesting techniques of conformal field theory, not the machine strip. But first, before we get into before we get into formalism, let's try to study the answer in a slightly slipshod way. Okay. So what's our goal? Our goal is to take this action, which is minus t. Okay. Now I'm going to switch to the conventions used in string theory. T. What was t? The coefficient behind the action was the tension of the string. Right? In conventional, it's conventional to write T as equal to 1 over 2 pi alpha. Let's look at dimensions. Tension is mass per unit length. Okay? A mass, energy are all the same dimensions because h cross is 1. And mass and inverse distance, because c is 1. And mass and inverse distance are also the same dimensions because h cross is 1. Okay? So we've got mass per unit length, which is 1 over length squared. Okay? Therefore, this quantity, this alpha prime, is a quantity of dimensions length squared. Square root of alpha prime is a length, and is a famous length. It's going to be, we will encounter it all through our study of string theory. It's the length associated with the size of strings. It's called the string scale. Okay? At the moment, this is just a change in notation. But the square root of alpha prime will be the length scale that will appear all through our study of string theory. Okay. So t was this, but now our action was minus t by 2, so minus 1 by 4 pi alpha, right? Then integral square root of minus g del alpha x mu del alpha x mu. Okay, now we're supposed to understand how to deal with this action, treating reparametrization invariance and Weyl transformations as gains of interest. Okay, now what I'm going to do is, in order to quantize this theory in the fastest, yet honest, in an honest way, but the fastest way that I can, is use a mishmash of the methods that we used last class, all of which we understood very well for the case of the particle. The first thing I'm going to do is to use an analog of method number 4. The last method, if you remember, was to take an action that had a gauge symmetry, fix gauge, but be careful about dealing with the constraints that accompany the gauge fixing. Okay? So, that's it. So, what are our gauges? We've got reparametrization invariance. How many functions in reparametrization invariance in 2 dimensions? How many functions worth of invariance? 2 functions worth of invariance. That's 2. And we've got Weyl invariance. How many functions worth of invariance here? 1 function. So we've got a total of 3 functions worth of invariance. Functions of the worksheet worth of invariance. It should be possible to use these 3 functions to set any 3 other dynamical functions to be something specific, up to possibly discrete ambiguities or something like that, which we'll deal with carefully in the next few things. Okay? So, what we're going to try to do is to set this G alpha beta, okay, G alpha beta to the form e to the power phi eta alpha beta using reparametrization invariance, and then to set the same thing to eta alpha beta using Weyl. Now there are immediately questions of, can you do it? Can you always take any metric and use reparametrization invariance to set it to this form? After which, of course, you can always set it to this form. These are interesting questions, which depend on many details. It depends on the space in which you're living, and so on. We will analyze all these questions in detail in a few lectures. But for now, we're going to forget some subtleties. They affect small things, but not gross. Yeah? And pretend we can always do it. Okay? Pretend we can always do it. So this is the gauge that we're going to set. Okay. Once we have set our gauge, our action becomes enormous extremes. Our action becomes s is equal to minus 1 by 4 pi alpha prime square root of there's no minus g now, so it's just del alpha x mu del alpha x mu, where the contraction is now done using the flat space metric in 2 dimensions. Okay, this is a system of 3 bosons in 2 dimensions, which anyone can solve. Okay, great. But of course, in fixing gauge, there are 2 things you have to worry about. Okay. The first thing we have to worry about is the constraints that were associated with this gauge fixing. Okay, so let's worry about that. Now, the constraints associated with the gauge fixing were the equations that Jyoti is going to write for us in this class. They were the equations of motion with respect to the objects that being fixed, which was d alpha x mu, d beta x mu is equal to square root of g, but that's now since square root of g is just 1, or square root minus g is just 1, we have minus half del alpha x mu del. Oh, there was no square. This is g alpha beta del alpha x mu del alpha x mu. Okay, so we have to do our quantization consistent with these constraints. So these are constraints. Right. Okay. Now, in order to understand what these constraints are, it's useful to use a nice set of coordinates on the world sheet of the string. Okay? So the coordinates that I'm now going to introduce to you are the like coordinates of the world sheet of the string. So far we've been using these coordinates sigma and tau, in terms of which we have chosen the metric, or let's say tau and sigma, in terms of which we have chosen the metric to be -1 and 1. Okay? But let's now move to a new set of coordinates, sigma plus, which is tau plus sigma, and sigma minus, which is tau minus sigma. And let's write everything on the worldsheet string, everything in action, in terms of these variables. Every derivative in terms of derivatives for sigma plus and sigma minus. So we're going to transform this action into that form. That's very easy to do. So let's remind ourselves how things work. Firstly, about the action. Okay, this thing was minus del tau squared of x plus del sigma squared of x. But there was a minus sign, so that's a plus and minus. Okay, but there's minus signs, so this is plus and minus. Okay, and now let's rewrite this into, let's see if we can find a simple expression in terms of plus and minus derivatives of x that gives us the same thing. Well, so let's see. So del tau, so let's use the chain rule of partial differentiation. So suppose you've got del A, this is the same thing as del xa by del yb d by d xa. Okay? Now we know what x plus. Okay, so this tells us, for instance, from this condition that del plus is equal to del tau plus del sigma. That's the other way around. Let's use the chain rule. Let's use it right. dyb by dxa d by dy. Okay, so let's choose our y's to be sigma plus and sigma minus, and our x's to be the taus. So taus and sigmas, we have del tau is equal to del plus del minus, and del sigma is equal to del plus minus del plus. Right, because del sigma by del tau is 1, del sigma plus by del tau is 1 plus. Okay? So you can take this and plug this into here to see that this is the same thing as del plus x del minus x, and I think by 4. This is the same thing as del tau x tau squared minus del sigma x tau. Yeah, the 4 is because you get a factor of 2 when taking this square, factor of 2 with the other side, this square, so you get 4 times that, you just plug in here, and that's why you need to work. Okay, so triviality, but okay, let's keep it. Let's try to get all factors straight. Okay, so our action rewritten in terms of plus and minus has the following interesting form: 1 by pi alpha, right? The minus we absorbed, and the 4 I've just cancelled, and del plus x mu, del minus x mu d2. 1 by 4 should be on the other side. Let's see. Very possible. Let's see. If we put in what? Yeah. And now is that consistent with that? Yeah, it is consistent. Sorry. Good. Okay, so that's what our action looks like. Let's see what our constraint looks like in a moment. Okay, this form of the action is sort of nice because it helps us solve the equation of motion very simply, as we'll see in a moment. And I'm familiar with the wave equation. But okay, the real reason for going to these variables is that this constraint becomes much simpler. So let's look at what the constraint looks like. Okay, so this constraint here was of this form in any set of variables. So let's use it in the variables where alpha, beta range over plus and minus. Okay? So in order to use it, I need to know what G alpha beta is in terms of plus minus. Okay. But minus V tau squared plus V sigma squared is just identically the same as minus of D sigma plus D sigma minus. A plus B, A minus B is A squared minus B squared. Okay? Which tells us that G plus minus is equal to minus half. There's a factor of half between what we've got here and what we've got here because the metric is symmetric. There are two terms. Because G plus minus is the same as G minus plus. Which tells us that G plus minus, if we need that, is equal to minus of 2. When we invert. Okay. So now let's compute this constraint equation. Let's compute this constraint equation. All three components of it. Well, the first thing we see is that the plus components and the minus components. So let's write the constraint equation as this minus this, and we can see it. The plus components and minus components are very simple. They're very simple because in our new set of coordinates, G plus is 0, G minus is 0, so we get no contribution from this term. Is that right? So when I say G plus minus is out, I should supplement that by G plus equals 0, G minus. Is that clear? Okay? So two of the constraints are very simple. The del plus of x, x mu, del plus of x mu is equal to 0, and del minus of x mu, del minus of x mu is equal to 0. What is the third constraint equation? What is the constraint equation that we get by taking plus and minus? Can somebody do it without doing algebra? We've already set the answer. It's 0. So as Loganaya pointed out, by taking the plus minus component in this coordinate system, we're taking the trace of the metric of these equations. And we've already seen that should just not give us an equation, that should be an identity. Now it's a matter of keeping your wits about you. Let's try to see that it actually works. That it's a matter of 2's and minus signs. Let's see if we're good enough. Okay, G alpha beta is minus half. So that's okay, great. So let's look at the plus minus equation. So the plus minus equation is del plus x mu, del minus x mu on the left hand side. Then we have minus of 1/4, because minus of half, and then keep up minus half. That's G alpha beta. And then this quantity. Now this quantity was what? It was del plus x mu, del minus x mu, multiplied by G plus minus. But there were two such terms. Because del plus x mu, del minus x mu, and del minus x mu, del plus x mu. So two such terms, and G plus minus is minus 2. So we get into minus 4 times del plus x mu, del minus x mu. Not that, I think we've got it. Okay? So minus 4, 0. Okay? So, in this coordinate system, it becomes explicit that there are two rather than three constraints. There's the plus plus constraint, the minus minus constraint. The minus plus constraint is nothing. Okay. Fine. So, let's summarize. What have we got so far? We've understood that what we want to do is to quantize the action that I've written down here. Quantize this action. Okay. Subject to okay. But before we actually go ahead and solve this problem, there's one more irritating but important point that I have to emphasize to you. And that's the following. You see, we discussed at the beginning that there may be subtleties about reaching this gauge. Okay? And we talk about the effect that those subtleties have as we get to that part of the course. But there is a more important question that has important effect on quantization, so we must talk about it now. And that's the question of, once we have reached this gauge, have we completely exhausted our coordinate freedom? Our gauge freedom or not? Do we have additional gauge redundancy left once we have reached this gauge? Okay? Now, let's see. Suppose we were asking the question in general relativity. We've taken a metric and made it flat somehow the other, just sigma. We asked, are there coordinate redefinition, are there coordinate changes that commute with it being flat? And there are only the very trivial ones, like Lorentz transformations. Such things, such small numbers of things won't affect anything. But remember, our gauge freedom here was not just coordinate redefinitions, with coordinate redefinitions plus Y transformations. Okay? So, if we perform a coordinate change that doesn't leave the metric invariant, but whose only effect on the metric is to rescale the metric by an overall function, then that rescaling of the metric can be undone by a Y transformation. So that is also a gauge symmetry now. Okay? So any change of coordinates, any reparametrization of the theory that whose effect is to perform an overall rescaling of the metric, okay, in this gauge, okay, is a symmetry that we have not yet fixed. Is this clear? Such coordinate changes have a mathematical name. In infinitesimal form, they induce by what I call conformal killing vectors. So a mathematician would ask, for a mathematician, we're studying the problem of finding all conformal killing vectors in our system, though mathematicians would generally tend to impose conditions at infinity for these vectors. For the local questions we're asking now, we're not imposing conditions. Okay, so now we're going to ask the question, can you think of any reparameterizations in two dimensions that change the metric, of course, change the flat metric, but change the flat metric only by multiplying it by an overall function? Now, I know several of you know the answer, but for somebody who doesn't know the answer, because you've read it before, can you think of any such function? Any such reparameterization? Okay, multiplying by a constant is an example, but there are many more. In order to help you, let me rewrite the metric in our nice coordinates. D sigma plus, D sigma minus. This is our metric. Now, can you think of any changes of coordinates that only multiply this metric by an overall function? You see, what's the characteristic feature of this metric? Characteristic feature is that it has zeros here and then something here, because it's symmetric that something has to be the same. All you want is some change of coordinates that will leave the structure intact. By which I mean there is no d sigma plus term, no d sigma minus term, just as d sigma plus d sigma minus. Can you think of coordinate change in this metric that achieves that?
Sigma plus should go to the function of sigma plus.
Very good. Sigma plus being redefined to any function of sigma plus, sigma minus being redefined to any function of sigma minus preserves this. Okay? So there is an important function worth of ambiguity, function worth of not yet having fixed our gauge freedom completely in our problem. There are sigma plus is equal to some function, let's call it f of sigma plus, and sigma minus is equal to some other function, let's call it j of sigma minus, are functions worth of reparameterization invariance that we have not yet fixed. Okay? Now, you might think, well, what happened to our argument? We used 3 functions to fix 3 variables. I mean, maybe there's some discrete ambiguity in that, or some small ambiguity, but how are we left with functions work? Is the question clear? Sounds unreasonable to be left with as much freedom as you thought you'd fixed. What's the answer to that?
Constraint equations is also changed.
No, this is an equation independent of constraint equations. Just you're fixing gauge. The answer to that is that we're not left with as much freedom as we fixed, because these are functions of one variable, not two. You see, our general coordinate transformations had as reparameterization invariance 3 functions of 2 variables. What we're left with is 2 functions of 1 variable. That's much less. So measure 0 instead of functions of 2 variables. Okay? But yet might be physically important. Is this clear? Okay. So before we just embark on a mathematical program of quantization, we have to deal with the fact that we have not yet fixed all our gauge symmetry. So let's put that as point 3. Need to fix unfixed gauge symmetry. Need to fix unfixed gauge symmetry. Sigma plus is equal to f of sigma plus, sigma minus is equal to g of sigma. Okay. Now, in order to emphasize to you, in order to do this fixing, and also in order to emphasize to you how important this fixing is, before proceeding to the quantization, I'm going to remind you of the classical solutions. The classical solution of this problem. Okay? So what do we have? Well, suppose we were to compute the equations of motion. Suppose we were to compute the equations of motion for x mu, we vary the action and we find del plus, del minus of x mu is equal to 0. It's a very familiar equation of motion. It's the traveling wave solution in 1 dimension. And we know that all solutions to this equation of motion are x mu is equal to, let's call it x mu plus of sigma plus x mu minus of sigma minus. As you can easily prove this. This is a set of solutions to the equations of motion. Of the equation. Now, are these functions x plus and x minus completely arbitrary? But remember, we were dealing with a string such that whose sigma coordinate was periodic in 0 and 2, between 0 and 2 pi. So it's not completely arbitrary. These functions have to be periodic in sigma plus and sigma minus, with periodicity 0 to 2 pi, which tells us that if we wanted to, we can expand them in a Fourier series with only the correct integer frequencies. Okay, we'll come to that. We'll come to the detailed solving and quantization of solutions in a moment. But why I wanted to say this immediately was to emphasize how important that remaining remaining gauge redundancy is. You see, suppose I take this gauge transformation and I apply it on a solution. Of course, I must get another solution. Okay? So what do I get? I get the sigma plus replaced by f of sigma plus, sigma minus replaced by g of sigma minus. Okay, but you see, if we were interested in looking just at the space of solutions, we could use this coordinate redefinition ambiguity then to set any particular one of these x's to something specific. We could just use any function of sigma plus is as good a definition of sigma plus as sigma plus itself, provided there are certain global things that doesn't tell that out. Right? So we have a coordinate redefinition of ambiguity in our problem. Sigma plus is only defined up to functions of itself. Sigma minus is only defined up to functions of itself. Now, on shell, solutions to the equations of motion, these things are divided up into functions of sigma plus and functions of sigma minus. Okay? So, one of these coordinates could be used as a definition of sigma plus. Okay? To say it again, even before we impose any constraints, the space of inequivalent classical solutions is not, suppose we went in d dimensions, d space-time dimensions, is not d functions of sigma plus and d functions of sigma minus. It's d minus 1 functions of sigma plus and d minus 1 functions of sigma minus. Is this clear? Okay? The constraints, on the other hand, remember the constraints have this nice property that you got one constraint for pluses and one constraint for minuses. Del plus a function of sigma minus is 0. So the first constraint constrains x pluses and the second constraint constrains x minuses. Okay? So the constraints, on the other hand, are one more equation on sigma plus. So it can be used to eliminate one more solution. So the space of classical solutions of this problem, is 20. Is d minus 2. Is d minus 2 functions of x plus and d minus 2 functions of x plus. Okay? If we had forgotten about the solution, this redundancy, we would have got the answer d minus 1 and d minus 1, which would be totally wrong. Okay? So it's a very important thing as people soon see. Now, can somebody give me a physical interpretation of d minus 2? So let me ask you the following question. Suppose I have a long string, stretched in a physical three-dimensional space. The string has tension, and I hit it a little bit. The oscillations of the string can be thought of as some number of scalar fields propagating on the string. How many scalar fields in physical space? Say it louder. The camera should hear you. That's correct. It's 2. The transverse oscillations can oscillate that way, or can oscillate that way. You might have thought it should be 3, because the 3 directions in space. But one of the directions is the direction in which the string is itself. It can oscillate there. Okay? In a physical string, you might be able to oscillate that. There might be pressure. But that's what kind of string this is. The only, there's no sense about which part of the string is going. It's just a word line occupied by the string. So there's no sense in oscillating in the direction of the string. That's meaningless. Okay? So the number of oscillations in our problem should be d minus 2. That's what we're finding. And it's very good because nothing else would have made sense.
Assuming that the number of non-perfect spatial reflections is 3, right?
Well, in the little toy question I gave you, that was the assumption. But you can easily in your mind now height that up to d space-time dimensions. And the answer will be d minus 2. You can't oscillate in time, you can't oscillate in the direction of the string. The remaining directions you can oscillate. So that's d minus 2. Is this clear? Fine. So that's all I wanted to say about rough analysis of classical motion. Now we're going to use all the intuition we've gathered to try to perform a quantization of the string. But questions or comments before we proceed? Questions, comments?
Can you just go over the argument for d minus 2 quickly again?
The physical argument or the argument formally?
The physical argument.
The physical argument was this. See, suppose you've got a string occupying a certain position, and you have to ask what you want to write.
There are no invariances. Translational invariances along the string, or
there's no necessary translational invariance along the string. But you see, if you ask where can a little bit of the string move, it can move in that direction, or it can move in that direction. If it moves here, that is changing the shape of the string, and so it's not counted as a new shape. You see, because only degree of the variables of string theory are what path in space-time the string occupies. There's no sense of what part of the, our string isn't made up of atoms we can label. There's no question of which atom is where. The only thing we can say about a string is what space-time curve it is occupying. So if you try to move the string along its own shape, that's not changing that space-time curve. Is this clear? Okay? That's the physical argument, and we've seen it formally from here, and we will see more clearly as we go.
Also, the conformal images that we have here, I mean, the scaling of this function that we have here.
Yes.
Is a consequence of this Y symmetry and the parameter.
Exactly.
In this particular case, right?
In this particular gauge. You could choose some crazy gauge in which these symmetries have completely different consequences for that gauge. Yes, but Dr. Moy's comment was completely right. You see, we argued that coordinate transformations whose only effect was to rescale the metric are a symmetry of an unfixed reparametrization plus wild symmetry of our problem. There's a second name for coordinate transformations whose only effect is to rescale the metric, and that they call conformal transformations. So something that we concluded just on general grounds is that the theory of the world sheet of the string, this theory that we're studying, must be conformal field theory in the gauge symmetries. Okay? Very good. Other questions or comments? Fine. So now let's move on. Okay. So in order to do the quantization, of course, we first have to deal with the unfixed gauge symmetries, the unfixed gauge symmetries of our problem. Okay. So before we actually start doing it, I want to give you one bit of orientation. You see, the orientation has to do with the nature of phase space in any classical system. Phase space is something that you are familiar with as a space parameterized by positions and momenta of the dynamical variables of the system. But that's just one way of describing phase space, and not the best way, not the best and most invariant way of describing it. So why are we interested in positions and canonical momenta? We're interested in positions and canonical momenta because they constitute the full set. Once you take out all constraints that happen to be in the problem, they constitute the full set of initial conditions for classical dynamics. Okay? As you know, specify a coordinate and a velocity. Velocity is essentially moment. Okay? But initial conditions are in one-to-one correspondence with the solutions of the theory. For every initial condition, there's a solution. So the best way to think of phase space is to think of it as the space of classical solutions of the theory. Okay? That's what the phase space of the system is. It's a space of classical solutions. Okay? And when you quantize phase space, where quantization is a procedure of associating an operator algebra, Hilbert space operator algebra, with phase space. So there's an intimate, of course, connection between the classical motion of the system and the quantum motion of the system. The connection, in one way of phrasing it, goes through find the set of all classical solutions, that's phase space, and then quantize the phase space. Okay? So that's the procedure we're now going to try to implement. We've already seen that the phase space of our system is made up of 24 functions of x plus, sigma plus, and 24 functions of sigma minus. So that's the quantization should reflect that problem. Okay, so let's now try to move more formally. The formal procedure goes like this. We see that we have, please. Oh, sorry. D minus 2. And I see yes. Now let's move forward. More formally. We've not yet fixed this gauge invariant. Okay? So let's fix it by choosing a particular slice of phase space. Okay? So on our space of solutions, we've got this equivalence that we talked about, and we want to fix this equivalence. So on the space of solutions, we've got the equivalence, and I'm going to fix it by doing something that you might think is a little weird, but it was hit upon by trial and error, and it's a good thing to do. Okay, so let me define x 0 minus x plus x d is equal to x plus and x d minus 1. 0 minus x d minus 1 is equal to x minus. Now this whole thing gets confusing because there are two things going on. There's space-time, the place where the string is moving, and there's the wordsheet of the string. X is, remember, coordinates for space-time. Sigmas are coordinates for the wordsheet of the string. The two are different. Okay? We use light cone variables, sigma plus, sigma minus in space, on the wordsheet. Now, we're going to do something a little weird. We're going to break explicit Lorentz invariance in space-time. Okay? What I'm doing now is analog of the second way of quantizing that we had yesterday. The way of taking this nice Lorentz invariant action and saying, well, let me use tau as time. Everything was very clear then, but it wasn't explicitly Lorentz invariant. Okay? So, in order to get at, in order to do the fastest route to quantization, I'm going to do that. I'm going to break explicit Lorentz invariance of the action by firstly choosing out one special spatial coordinate, the d minus 1, combining with x naught and say that's x plus, combining this with the minus sign and say that's x minus. So far I've done nothing to relabel coordinates. But where I do something is saying, let me choose the gauge to, on the space of solutions, fix my reparametrization immediately. Let me choose the gauge. So x minus is equal to alpha prime p minus tau. Okay, this is the final gauge I'm going to fix, but I'll say it in a way that makes it sound less arbitrary. Firstly, what is p minus? At the moment, it's some undetermined number. I will convince you in a moment that p minus cannot be fixed. We don't have the freedom to rescale p minus. That's not the solution. So we need an ambiguous number that parameterizes different p minuses give you different solutions, physically different solutions. But let me write this better as x minus plus the right moving part. Okay, we're clear. Yeah. X minus plus is equal to alpha prime p minus into sigma plus by 2. And x minus minus is equal to alpha prime p minus into sigma minus 2. Remember, every solution to the equation of motion was some function of sigma plus and some function of sigma minus. Okay. This statement, how do I make tau a function of sigma plus and sigma minus? Well, tau is equal to sigma plus sigma minus by 2. Okay? So, rewritten tau equals sigma plus sigma minus by 2. And then I've used that to identify what I meant by. So, this statement is equivalent to this statement. Is this clear? Okay? So what have I done by making this gauge fixing? What I've done is to say, well, remember x plus of minus was in general an arbitrary function of sigma minus. And I'm going to choose my reparametrization freedom to say that function of sigma minus is now sigma minus times a constant. Is this clear? Is this clear? My read? No. You see, what did I have in my hand? I had reparametrization of variance. Just changing sigma plus to any function of sigma plus. Okay, but now on the space of classical solutions, I have d different functions of sigma plus. x1 is a function of sigma plus, x2 is a function of sigma plus, all the way to xd minus 1 is a function of sigma plus. Okay? Now, in studying classical solutions, I could choose the following gauge. Suppose there were these d different functions of sigma plus, but I could use my sigma plus reparametrization immediately to choose any one of those functions to be my new sigma plus. Once I've done that new function is I've done it with x minus actually. It's x0 plus xd minus 1. That's algebraic convenience. I could have done it with x0. Conceptually, I could have. This is just algebraic convenience. Okay? Fine. So that's all I've done. I've taken x plus and said whatever that is, that's my new definition of sigma plus. Up with this constant. We talk about the constant. And whatever x minus was, you see, that's the problem with talking about this. There's a minus and a plus and a minus and a minus. x minus plus for sigma plus, x minus minus for sigma minus, up to a constant. Okay? I'm using this reparameterization ambiguity to do this. Now, is this clear? This is p minus and p minus are just this is just some number which we can find. Okay, now why this number? Why could I just set it to be sigma plus? The point is that our reparameterization ambiguity wasn't complete. Because there's one thing about the sigma coordinate that we know. Namely, that all functions are periodic with periodicity 2 pi in sigma. Okay? And you should know what coordinate change you do that. Should change that. Okay? So if in some variable your functions were periodic with periodicity 2 pi, if you make a coordinate redefinition that respects that periodicity, then you're safe. But if you make a coordinate redefinition that breaks that periodicity, then you're not. For instance, a rescaling of sigma breaks the periodicity. Because it takes periodicity 2 pi to periodicity 2 pi times the rescale amount. Okay? But if I were to try to change this constant here, what I would be doing is changing each of these functions by a constant. But the variable sigma is just, sigma plus minus sigma minus. So that would also be changed by a constant. Okay? So I don't have enough coordinate redefinition freedom in my hand to soak up the zero mode part. The zero mode part of what x minus was doing. Is this clear? Let me say this there. Let's remember we said that the most general solution, okay, of any of these x's and therefore of x minus was of this form. Let's forget about the x sigma minus in what I'm saying for a moment. Look at just sigma plus. Okay? Now, this was a periodic solution. So x mu, what we have is that x mu plus can be written in terms of Fourier modes. So we could write this as n not equal to 0 e to the power I n sigma plus times some number. Let's say beta to the power n. Right? Sorry? Okay? Now, in addition, of course we don't need n not equal to 0 to be constant, that's fine. So, sum over all n. But there's one more thing we can do that also solves the equations of motion. Apparently. Okay? And that one more thing that we can do is to add to it a constant times sigma plus. Well, now this doesn't respect the symmetry, because when you take sigma plus 2 pi, we can add to this plus some constant times sigma plus. This by itself doesn't respect the symmetry. But remember, we also had x minus in our hands. So if we chose a constant in x plus and the constant in x minus to be the same, then the sigma part cancels between the two. You see, x is then just a function of tau. And then it does respect the symmetry of the problem. Okay? So, we are only going to allow ourselves redefinitions of sigma plus and sigma minus that respect the periodicity of sigma, which allows us to set all these terms to 0, but doesn't allow us to fool around with this term. Okay? So this constant, whatever it is, can't be changed. Okay? So this is a physical object, and I've called it P minus. Why I call it P minus will become clear very soon, but at the moment it's just some number, parameterizing different inequivalent solutions. Is this clear? So I have now looked at the phase space of my problem, namely the space of all inequivalent classical solutions, and characterized it by solutions of d minus 1 different functions of sigma plus and sigma minus. Okay, because I've set one of these functions to something specific. It's not quite something specific. There's a number which parameterizes inequivalent solutions. Is this clear? Okay, great. Now, the next question I want to ask is, now that I fixed this gauge now that I fixed this gauge in my theory, can I just plug it into the action? Or do I have to worry about the equivalent of the constraints that come from fixing this gauge? Is this clear? That's the question. Now, let's see. The constraints from fixing a gauge are always the equations of motion that would have followed had you not fixed this gauge. So we want to know what are the equations that come from varying x minus. Can somebody tell me what are the equations that come from varying x minus? X minus where minus is in space. The minus component is in space. You get an equation for x plus. Exactly. So the equation of motion that comes from varying with respect to x minus, as I'll leave you to check, is the Laplace equation del plus del minus of x plus. Okay? So, if we were just to plug in our solution into the action, that would be fine if we were already also to impose this condition that x plus satisfies the Laplace equation. It's a function of x, sigma plus, sigma minus. However, now we're in luck. We're in luck because we don't independently have to specify this constraint, because it follows from the earlier constraints that we had. Remember that our earlier constraint was del plus. Well, okay, maybe that's inaccurately said. But maybe it's more accurate to say the following. Suppose we do impose this as a constraint. We say that x plus is a sum of sigma plus and sigma minus. Then that function of sigma plus and sigma minus that we get for x plus is completely determined by the other constraints that we have. Okay, why is that? Okay, see, we have what are the constraints look like? The constraints look like del plus x minus plus sum over I del plus of xi del plus of xi, where I runs over all the remaining d minus 2 coordinates, the coordinates that are not plus or minus. Okay? Now we've chosen fixed gauge such that del plus of x minus is equal to alpha p minus by 2. So, we have been told, therefore, that del plus of x plus is equal to 2 by alpha p minus into sigma of I del plus xi del plus xi. Okay? So if we just treat this as the solution, if we just treat this as the solution of what x plus is, given what the other i's are doing, that solution automatically, obviously obeys the fact that it's a function only of sigma plus. The minus part of it obeys the fact that it's a function of sigma minus. Okay? So, now what have we done? We've used the fact that we know that x plus must be a function of sigma plus and sigma minus only. Put in that fact plus the earlier constraint to completely solve for x plus in this gauge. Completely solve is a little inaccurate. We have not solved for the zero mode of x plus. You see, we only have solved for that part of x plus that is visible in the derivative expansion. But x plus will have constant piece. There's some constant piece that we have not solved for. But almost, apart from that one constant term independent of sigma plus, we've completely solved for x plus in terms of the motion of the other d minus 2 coordinates in this case. Is this clear? Okay? Questions or comments about this? Fine. So, now we're going to ask the question. Having done all this babu-ba, can we now write down a simplified action, okay, for a dynamical system that has the same solutions, that is dynamically equivalent to the system that we started with. Namely, an action that has all the same solutions, an action that has all the same solutions to the equations of motion as the one we want. Okay? Well, you see, because solutions to the equations of motion are parameterized just by xi's and by this one number p minus, also by some 0-1 part that we start in a moment. Okay? If we were interested in writing down an efficient action, that action should just not have x plus and x minus in it. Okay? Maybe another way to say it is take the action of the theory that we had and just plug in the gauge condition. Okay? And check to see whether varying the equations of motion that follow from that action, are the equations, give us the solutions that we want. Okay? So, I may have said this confusingly, let me say it again. If we took the original action that we had and we plugged in our gauge condition in alpha prime x minus is equal to constant times p minus times tau, okay, then the only thing we're losing from that is the equations of motion that follow for x plus. However, putting in those equations of motion, saying that x plus is a function of sigma plus and sigma minus independently, plus the constraints allow us simply to determine x plus. This whole process does not back react on xi's. Okay? The full classical dynamical system is an arbitrary left moving, right moving functions of xi, and all that the system does is determine what x plus is doing in terms of what xi is doing. Okay? So basically, the conclusion we've reached is that it would be legitimate in this situation just to take the action we had and plug in our gauge. Okay? Once we've done this, we can even forget about our constraint equations. Because the constraint equations don't constrain the dynamical degrees of freedom that remain. Just relates other degrees of freedom to these guys. Why do we care? Okay, there is one degree of freedom that we would be wrong in doing this with, which we come to. Okay, so let's move. So what we conclude? So we had 1 by pi alpha prime. Okay. Okay, let me go back. So our action was equal to 1 by 4 pi. Okay, let's write it. 1 by 4 pi alpha prime, and we had x mu dot minus x mu prime. It is equal. This was our action. Into this action we put the gauge condition. Okay? Into the action we put a gauge condition that I'll come back to 0 modes in a moment. But that essentially eliminates, what does it do? It makes we put in a condition such that x. So there is part of this that is x plus x minus, and there is part of this that is xi xi. Okay, let's start in the x plus x minus part. You see, all that survives here in the x plus x minus part are 0 mode contributions. You see, suppose you took x plus and Fourier expanded it in modes of the circle, and x minus and Fourier expanded in modes of the circle. We set all the non-trivial, non-zero Fourier modes of x minus to 0. But in this integral, the only way you can get something non-zero is that a Fourier mode with momentum k clicks with a Fourier mode with momentum minus k. So the action that remains is an action only for the 0 modes of x plus and x minus. Is this clear? So there's no action remaining for the oscillator modes of x minus, that's why it can be with gauge fixed at 0, or the oscillator modes for x plus, they just don't enter the action. Okay? Xi's are just not affected by what's going on. So the final conclusion that I come to, that I want to draw is the following. Is what following. Is, see, if you take the action 1 over 4 pi alpha prime, if you take the action 1 over 4 pi alpha prime, x plus dot x minus dot times 2 pi integral dt plus d2 sigma xi dot squared minus xi prime squared close bracket. Okay, then this is the full dynamic action for the dynamical degrees of freedom left. Okay, this is the full remaining, full action for the degrees of freedom of interest. Okay, what was this x dot and x minus? These were 0 modes. So we took x and we expanded this as just a function of sigma now, not sigma tau. We took x plus and we expanded it as x plus the sum over n x plus e to the pi n sigma. We've already argued that all the modes with non-zero n drop out. This is the mode with n equals 0. The 2 pi has come from doing the integral over sigma. Yeah, in 2 minutes. Okay, great. Okay, so sorry. So what? Okay, so the net conclusion then is that we're interested in the action 1 over 2 alpha prime x plus dot x minus dot plus 1 over 4 pi alpha plus 1 over 4 pi alpha prime xi dot the whole thing squared minus xi prime the whole thing squared d2 sigma. Okay, this action is to be supplemented with one remaining constraint. The one constraint that was not completely redundant when we did this whole thing. That one constraint is the 0 mode part of this constraint. Why is that? Why is that this one constraint is left behind? Okay, the one constraint is left behind basically because of this. You see, as we will see when we do the quantization of the system, this one solution couples to one degree of freedom in x plus. Okay, so that part of x plus is not redundant. Namely, when you look at the symplectic form, the Poisson brackets between degrees of freedom in our system, x plus oscillators have Poisson brackets with x plus oscillators. So by throwing away x plus, most x plus degrees of freedom, we're not doing anything bad. However, the 0 mode of x minus couples with the 0 mode of x plus. So if we want a quantum system, we want to build a quantum system out of a classical system that has solutions parameterized by a number in the 0 mode sector of x minus. We need to include in that quantum system the 0 mode of x plus. Okay? And the remaining constraint, the one remaining constraint, is going to allows us to, gives us the constraint that links the dynamics of the 0 mode of x plus with the 0 mode of x minus. Okay, so we've basically run out of time, and I know this has been confusing. It's been confusing for 2 reasons. Okay, it's been confusing for 2 reasons. One of which is that we're trying to take shortcuts. We're trying not to give the full detailed justification, okay, of the result we're trying to reach. Okay? Now, that is of course a very unsatisfactory way to proceed, and it won't remain that way. In the next few lectures, I'll give you a much better derivation of this action. Nonetheless, the way physics is actually done is it's only 20 years after the work is originally done that people come up with good derivations of the results. Okay, so it would be silly to not pay attention to slightly shady but intuitively correct ways of proceeding, because that's how you always do physics. Okay, so what I would like is all of you to think through everything we've talked about today on its own terms. Okay, and think about it and come with questions next class about it. Okay, in the first 10 minutes of the next class, I'll review the logic of what we went through, and then we will start by using this to derive the spectrum of the Bosonic extract. Okay, actually, the second reason I think it's been confusing is that the logic of this procedure actually relies on a way of thinking of systems, on the way of thinking of the phase space of a system that's slightly non-standard. So, okay, please think about this as carefully as you can. In the first 10 minutes of the next class, we'll have a question-answer session where we'll review the logic in detail, and you will attack it, and I'll try to defend it. Okay, great. Thank you.
So you're saying the main result is this action over here, right?
The main result, anything, this action supplemented by the zero mode of this condition.